So again, we already talked about this, but there's two possibilities that we have when we're working with our analyses. And the first is, pardon me, the first is when we have a p-value that is specifically less than alpha. The consequence of this is that we would then reject the null. So the decision in a case like this is that we reject the null. And that is the only option we have. We can reject the null, or we can fail to reject the null. So in other words, not reject the null. It's not reject the null or accept the null. It's only reject the null or fail to reject the null. So that's the first of the scenarios. The second scenario is the opposite of that, which is that the p-value is actually greater than alpha. And in this case, what we say is we would actually fail to reject the null. If you want to, you can actually write it in this code, because we're essentially, for all practical purposes, if we fail to reject, some would argue that that's the same thing as accepting. It's not quite, but that generally is the idea that people walk away with when they think about these. So this is the scenario that we have. So and the examples, the two examples that we have are if we have, we always are looking at the p-value. Now, again, what we saw in the conversation yesterday is that there's a couple ways we can actually think about this. So we can also think about, instead of p being less than alpha, we could say that the test statistic is in the critical region. That would lead to rejecting the null. Whereas if the p-value is greater than alpha, that means the test statistic is not in the critical region, and we would fail to reject. So that's just another way of restating what we're doing, what we're capturing here with the p-value. So essentially, if this is the idea of, if the null is true and we find something in this category, that means we've seen what would be considered a usual occurrence if the null were true, so there's no evidence to reject it. This is the scenario when there's an unusual occurrence, and in this case, we actually would then consider rejecting. All right, so that was the first of the discussions we did yesterday. So let's do the next one, which was talking about one-tailed and two-tailed tests, and when we actually do these. So I'm going to go ahead and clear this screen. So what we're talking about now are critical values, and this is the main idea for when we're working with critical values. Go back to the larger font. I like the larger font. So we're working with critical values. And the idea is, what are the formulas for a one-tailed or a two-tailed test? So let's write out the formulas for a one-tailed and a two-tailed test. So the first formula, so let's go ahead and do this. All right, so we'll do the following. I'll draw the following table. All right, so we're going to first talk about one-tailed and two-tailed tests. And we want to emphasize what are the formulas that we would actually use for each one. So let's go ahead and do the formulas for when we're talking about proportions. And generally when we're talking about proportions, in this case, we're really talking about z-scores. So anytime we're talking about z-scores, that suggests we're going to use the normal distribution. So for a one-tailed test, oh, sorry, I just realized something. I didn't put the lines in here. I'm going to go ahead and draw these lines in. All right, so if we want to get the one-tailed value, the formula for that would be equals norm S_inv, and then we would give the value alpha. Now I'm going to go ahead and write this in because I actually want to, there's a reason why I'd like to write this. Okay, let me give myself just a little more space to actually write it. So the norm S_in function Here we would actually just give it the value alpha. So we would go ahead and plug in the value alpha. So we plug in if we're looking for a one-tailed test, all of our significance is in that one tail. So we use the norm S in function. If we actually want a two-tailed test, if on the other hand we want a two-tailed test, then we actually need the following formula. So we actually need the formula alpha over 2. And I'll sort of emphasize this by making it extra thick. So alpha divided by 2, because in this case, oh, you know what? Sorry, I just realized I put that in the wrong spot. This is for a two-tailed test for this. This actually goes down here. So let me redraw that again. So we have alpha divided by 2. And the rationale for this is what we're doing is if there's a two-tailed test, alpha is our significance. That's the area that is actually in the critical region, or the probability of being in the critical region if the null is true. But we have to divide that over the two tails, so that's why we actually have to divide this by 2. Okay. All right. Now, for when we're talking about means, then we actually, when we're talking about means, we actually want to use we're talking about t ratios. Sorry. When we're talking about means, in this case, we're actually not talking about z-scores, but we're talking about t ratios. Remember, the t distributions are nearly normal, but they're not. The z-scores follow a standard normal distribution, which is indeed normal. The t ratios are very close, but they're not the same. All right, so in this case, we use the t in function. And if I want a two-tailed test, I just go ahead and enter equals t in alpha, and then I would give it my degrees of freedom. Now, again, in this context, we just give it alpha. That's all we have to enter here, and everything works out just fine. The reason here is because the t in function has been written to give us the two-tailed values. So it defaults to a two-tailed test, which means in the same way that I had to divide by 2 here to go from one tail to two tail, if I only want a one-tailed test and it's going to default to 2, I'm going to trick it and tell that my alpha is twice as large. So if I do the following, if I say equals t in df. So in this case, what I'm going to do is I'm going to say alpha times 2. Alpha times 2 will actually give us the desired result here. Okay, again, all we're doing is we're essentially just tricking the system to think that if we want all of alpha to go into one tail, so we'll trick it by telling it that alpha is twice as large, and then it will give us the critical value for that actual tail. All right, so again, that's sort of a review from yesterday. Now, here I focused more on just one-tailed versus two-tailed. Yesterday, we broke it down a little further and talked about left-tailed and right-tailed tests. But if you go with these formulas, if you just remember that for a left-tailed test, the critical value is negative, and the right-tailed test, the critical value is positive, you can use these values. This will always return a negative number. This will always return a positive number, and you just have to switch back and forth between which is appropriate based on the test that you're actually talking about. So let's just clarify that we know so let's just make sure we've got the idea of what a right-tailed and a left-tailed test are, and two-tailed tests in general. So I'm going to go ahead and save this. If there's no questions on this, I'm going to go ahead and clear this screen. And I'm going to draw a couple of normal distributions here, so bear with me. They are going to be pretty sloppy. So the first thing we want to look at, I'm going to try to draw 3 copies of this. So the first thing we want to look at is for a normal distribution, and we have it centered at some value. This again could be a mean or this could be, it's centered at some point, okay? And if we're working with the following, if we're working with the null hypothesis is that the mean equals a given number, and then the alternative hypothesis would be that the mean does not equal that number. Okay, or it could be, in this, I've written here mu, but this could be the proportion. This actually could be any sample statistic that we're actually interested in. In this case, if this is what I believe to be reality, or it's what I'm pretending to be is reality, this says that the mean is at this value. So I would actually be surprised if I found values, extremely large values up here. That would surprise me in the same way that if I found extremely small values down here, that would be surprising. And this is why we refer to this as a two-tailed test. Because we have alpha has been divided over 2 of the tails. Okay, the key indicator here, to be entirely honest, the key indicator that you're looking for is here. We're looking for that not equal sign. That's the clue that we have a two-tailed test. Okay. Alternatively, if we had a right-tailed test, so let me go ahead and draw a okay, so let me kind of draw a dividing line here. So we're going to draw a right-tailed test now. So again, let me get another sketch of my normal distribution. That's not what I wanted to do. Or I should have, since it's a lot not nicer than my curve. All right, so we got our bell curve now. Okay. Again, once again, we are centered at some value. Okay. Now for a right-tailed test, the alternative hypothesis is that the mean is greater than, or our sample statistic, our population proportion, population parameter, which I'll in this case as a stand-in we'll use the mean, is greater than that number that we're focusing on. That means the null hypothesis, which is the alternative of this, the null hypothesis would be that the mean is less than or equal to the given number that we have here. So if the mean is here or somewhere, some value less than this value, then I would not be surprised by values down here. Consequently, I would only be surprised by values that fall too far up here. And again, this is an example of what we call a one-tailed test, but more specifically, the tail is on the right, so it's referred to as a right-tailed. Okay. The indicator here is that we have, so I always encourage people to look carefully at the null hypothesis to see what would be surprising. But in this case, the fact that the mean is greater than, the hypothesized mean is greater than a value means we'd be surprised by very large values up here. Okay. And then last but not least, if we drew the third scenario, which is the left-tailed test. So here's the curve, here's the bell curve. They're getting sloppier, I apologize. Okay, here's the value. So in this case, the null hypothesis is that the mean is, our population mean is greater than or equal to some value, meaning my value is here or larger. So I wouldn't be surprised by values up here if I'm hypothesizing that that's where they might be. The alternative hypothesis, on the other hand, is that the mean is strictly less than that given number. So that means I would be surprised by values that fall in this region down here. And we're looking at the tail on the left, and that's why it's called a left-tailed test. Okay. Again, the focal point is here on the alternative hypothesis, where the mean that we're focusing on is hypothesized to be less than the value we're focusing on. again, these here are the, so if I were to highlight this even more specifically, these here are the one-tailed tests. So what I've highlighted here, these are all the one-tailed tests. Well, there's only two of them, either left or right, and this is the two-tailed test. Redraw it. So these are the one-tailed tests, and this is the only two-tailed test. The one-tailed test could be broken down right-tailed or left-tailed. In this case, the critical value is positive for a right-tailed test, it's negative for a left-tailed test, and it's both positive and negative for the two-tailed tests. All right, questions? All right, so let's just reemphasize a couple things then about the null hypothesis and the alternative hypothesis and how it relates to the both the claim that we're working on and this idea of quote unquote the condition of equality. So the null hypothesis. So the null hypothesis, we say the null hypothesis contains the condition of equality. Okay, now what do we mean by that? Well, it means something like the following. So if we're writing out our null hypothesis would look something like, oh, sorry, that's not the one I wanted. The null hypothesis would look something like this. H sub 0 would be the mean is, so it would be any of the following three scenarios. I'll sort of write them all out collectively, but it would be that the mean is less than or equal to a number, greater than or equal to a number, or specifically equal to that number. So these are what we mean by the conditions of equality. Equal to, that's very clearly a condition of equality, but greater than or equal to or less than or equal to are the ones that contain the other conditions as well. Now, again, we want to remember that what we're capturing here is this idea of the quote unquote straw man. So this is the idea, this is the straw man of the straw man argument. Most of the time, we don't actually believe this to be true. We actually believe the alternative hypothesis. So again, it's the alternative hypothesis that is usually the claim. Pardon me a second, I've got to. Okay, so it's the alternative hypothesis that is usually the claim. Oops. And again, usually, it's not always. So usually, what we mean by that, since it is we say it's usually the claim, what we're saying is that it is most often the case that we want this to be true, so we're testing the null hypothesis, which is our straw man. We did see an example yesterday where that was not the case. We did see an example where we actually had the null hypothesis was our claim. That was the example where we had the mean being, we said the class was adequately prepared. Adequately prepared meant a score of 12 or above. So 12 or above would be greater than or equal to 12. And that was a case where it was the condition of equality was in the claim itself. Okay, so but usually that's not the case.